Hi, I'm Quinn. Welcome to Daily Quantum Byte. Today we will explore superposition. People say a qubit can be in two states at once. And sure, that's the headline. But it's not the most helpful picture. The best intuition for superposition is actually much calmer. Superposition is what you see when you describe a quantum state in a particular measurement basis, like choosing a coordinate system. Let me explain with something familiar. Sunglasses. Light can be polarized. You can have vertical polarization, horizontal polarization, diagonal polarization. And if you put a polarizing filter in front of the light, the filter is basically measuring polarization in a specific basis. Now imagine a photon that's diagonally polarized. If your filter is vertical/horizontal, the photon doesn't look definite. It looks like a mix. Sometimes it passes, sometimes it doesn't. In that basis, diagonal polarization is a superposition of vertical and horizontal. But if you rotate the filter to the diagonal basis, the same photon looks completely definite. It passes with certainty. That's the punchline. Whether something is in superposition depends on how you measure it. IBM's learning materials say this bluntly. Superposition is in the eye of the beholder, meaning it depends on the basis you chose. So what is a qubit, really? Mathematically, it's a state that can be written as alpha times 0 plus beta times 1. Those alpha and beta values are amplitudes. When you measure, you get ordinary probabilities. The probability of 0 is the magnitude squared of alpha, and the probability of 1 is the magnitude squared of beta. But the quantum difference is that amplitudes can have phase, like arrows that can point in different directions, not just different lengths. And phase is exactly what makes superposition useful rather than just random. Here's the simplest way to feel that usefulness: interference. Start with a qubit in a definite state, like 0. Apply a Hadamard gate. Now if you measured, you'd get 50-50. So far that looks like a fair coin, but do not measure yet. Apply the Hadamard again. Now measure. You get 0 with certainty, ideally 100%. That is not what a classical coin does. A classical coin doesn't become perfectly predictable by flipping it twice. The reason the qubit becomes predictable is interference. The second Hadamard recombines the wave-like amplitudes so that the paths leading to the 1 outcome cancel out, and the paths leading to 0 reinforce. So superposition isn't the magic. The magic, if we must call it that, is that superposition carries phase, and phase can be engineered to create interference. One more intuition. Think of a qubit state as an arrow on the block sphere. North pole is 0, south pole is 1, and around the equator are equal weight superpositions. Different points on the equator can give the same immediate 50-50 measurement in the 0-1 basis, but they're still different states because they have different phase. That phase shows up when you apply more gates, and this explains something that confuses a lot of beginners. Two states can look identical if you measure right away, but behave differently after you do more quantum operations. That's because measurement throws away phase information. Gates can convert phase into probability differences. So when you hear a qubit is in superposition, translate it to, in the basis we're measuring, this state is a combination of basis states, and the combination has phase. That basis dependence isn't a footnote, it's central. A state can be superposition in one basis and definite in another, just like diagonal polarization looks mixed through a vertical filter but definite through a diagonal filter. Let's close with the practical takeaway. Quantum algorithms use superposition to spread amplitude across possibilities, then use phase shifts and interference to steer probability toward good answers. Superposition is the canvas, but interference is the paint. Next lesson, if you want to continue the chain, the natural step is measurement bases and why choosing the right basis is half the algorithm. That's all for today. Take care.